runs for a time slice, that is a process executes for a time slice, and when the time slice completes it is moved onto the ready queue. So, in order to achieve this round robin scheduling algorithm, which is also a preemptive scheduling algorithm. Now, in order to achieve the round robin scheduling, we need to configure the timer in the system to interrupt the CPU periodically. At every timer interrupt, the kernel would preempt the current process and choose another process to execute in the CPU. Let us discuss the round robin scheduling algorithm with an example. So, one difference with respect to the other scheduling algorithms that we have seen so far is the notion of time slice. So, this is the Gantt chart. So, especially see that periodically, in this case with the period equal to 2, that is we have keeping a time slice equal to 2, there is a timer interrupt that occurs, and the timer interrupt would result in the scheduler being run and potentially another process being scheduled into the CPU. So, a data structure which is very useful in implementing the round robin scheduling algorithm is the FIFO. So, this particular FIFO stores the processes that need to be executed next into the CPU. For example, in this particular case P 2 is at the top of the FIFO. So, it is the next process which gets executed in the FIFO. So, P 2 gets executed over here. So, for our example we will still consider the 4 processes as we have done before, that is P 1 to P 4, and we will assume that all of them arrive at the instance 0 and go into the FIFO or the ready queue, and they have burst times of 5, 4, 2 and 3 respectively. So, let us say for discussion that the scheduler starts off with this particular order P 1, P 2, P 3 and P 4. So, and it first chooses to execute P 1. So, P 1 executes for 2 cycles, and then there is a interrupt which occurs leading to a context switch, and then the top of the FIFO, in this particular case P 2 gets scheduled into the CPU, while P 1 gets pushed into the FIFO. So, P 2 then executes for 2 cycles until the next timer interrupt, in which case the time slice of 2 cycles completes, and then it gets pushed into the FIFO. So, P 2 now is at the bottom of the FIFO, while P 3 which is at the top of the FIFO gets scheduled to run. So, in this way every 2 cycles a new process may get scheduled into the CPU and execute. So, if we compute the average waiting time, so in this particular case we will see that the average waiting time and the average response time is different. So, what is the average waiting time for P 1? So, the P 1 executes 2 cycles here, 2 cycles here, and completes execution over here. So, it waits in the ready queue in the remaining of the cycles. So, the number of cycles it waits is 1, 2, 3, 4, 5, 6, 7, 8, 9. So, P 1 waits for 9 cycles. Now, P 2 waits for 8 cycles, 1, 2, 3, 4, 5, 6, 7, 8, P 3 for 4 cycles and P 4 for 10 cycles. So, the average waiting time is 7.75 cycles. Now, to compute the average response times, as we defined it before, the response time is the time the process enters into the ready queue to the time it begins to execute in the CPU. That latency would be the response time. So, P 1 for instance has a response time of 0 because it enters into the ready queue or enters into the FIFO and gets executed immediately. P 2 on the other hand enters in the 0th cycle, but gets to execute only after 2 cycles. So, it has a response time of 2. Similarly, P 3 enters at 0, but executes only at this point. So, at this instant, therefore, it has a response time of 4, and P 4 has a response time of 6. Therefore, the average response time is 3. Now, the number of context switches that occur is 7. So, in this case 1, 2, 3, 4, 5, 6, and a context switch occurs over here because the process P4 is exiting out and P1 continues to execute. So, the number of context switches over here are 7, that is 1, 2, 3, 4, 5, 6, and the 7th context switch occurs over here when P4 exits and P1 gets switched into the CPU. Now, let us take another more complex example of round robin scheduling, where we also have arrival times which are not the same. So, P1 is arriving at the 0th instant, P2 at the 2nd, P3 and P4 at the 3rd and 9th respectively. So, we can similarly draw the Gantt chart and the states of the FIFO for this case. So, to start with, in the 0th instant, the only process which has arrived is P1 and therefore, P1 executes for 2 cycles, and at this particular point when the timer interrupt occurs, no other process is present as yet. Therefore, P1 will continue to execute for another 2 cycles for another time slice. However, in this time slice we have 2 processes which have entered into the ready queue. These are the process P2 and P3. So, P2 arrives at this interval while P3 arrives at this interval, and they get added into the FIFO. So, at the second time slice completion, there is a context switch and P2 gets scheduled into the CPU to execute, while P1 which was executing will then go into the FIFO. So, P2 executes for 2 cycles, then P3 executes for 2 cycles, then P1 executes for 2 cycles, and at that time P4 has arrived and gets added into the FIFO. So, now we have 3 processes P1, P2 and P4, and these get scheduled to run over a period of time. So, the average waiting time in this case is 4.75, while the average response time is 2. So, how is the average waiting time 4.75? It means that process P1 has waited for 7 cycles. So, before it completes. So, that is 1, 2, 3, 4, 5, 6 and 7, while process P2 has waited for 6 cycles. So, it is 1, 2, 3, 4, 5, 6. Process 3 has waited for 3 cycles and process 4 has waited for 3 cycles. The average response time can be verified to be equal to 2, and the number of context switches was as before 7. Now, let us take the same example as we have done before, but with a time slice of 1, that is, we have reduced the time slice from 2 and we have made it 1. So, we see that in every instant we have a timer interrupt and potentially a context switch that can occur. If we compute the average waiting time and average response time for this particular case, we see that the average response time in particular has reduced. Why has this occurred? Is because once a process has entered into the queue, it has to wait for lesser cycles before it gets scheduled into the CPU. On the other hand, the number of context switches has increased from 7 to 11. Since we are having timer interrupts which are more frequent, therefore, there is more likely that a context switch will occur. Now, if we take the same example, but with a time slice of 5 instead of 1, and if we compute the average waiting time and average response time, we see that the response time increases considerably to 2.75, while the number of context switches reduces quite a bit to 4. On the other hand, we see that the scheduling begins to behave more and more like the first come first serve. The response time is bad because due to the large time slice, the scheduling behaves more and more like the first come first serve, which we know has a bad response time. So, from all these examples that we have seen so far, we can conclude that the duration of a time slice is very critical. So, it affects both the response time as well as the number of context switches. So, essentially if we have a time slice which is of a very short quantum, the advantage is that processes need not wait too long in the ready queue before they get scheduled into the CPU. Essentially this means that the response time of the process would be very good, or it would have a less response time. On the other hand, having a short time slice is bad, because we would have very frequent context switches, and as we have seen before, context switches could have considerable overheads. Therefore, it degrades the performance of the system. A long time slice or a long quantum has the drawback that processes no longer appear to execute concurrently. It appears more like a first come first serve type of scheduling algorithm, and so this again in turn may degrade system performance. So, typically in a modern day operating systems, the time slice duration is kept anything from 10 milliseconds to 100 milliseconds. So, XV6 programs the timer to interrupt every 10 milliseconds. So, the advantage of the round robin scheduling algorithm is as follows. The algorithm is fair because each process gets a fair chance to run on the CPU. The average wait time is low, especially when the burst times vary, and the response time is very good. On the other hand, the drawbacks of the round robin scheduling algorithm are as follows. There is an increased number of context switching that occurs, and as we have seen before, context switching has considerable overheads. And the second drawback is that the average wait time is high, especially when the burst times have equal lengths. The XV6 scheduling policy is a variant of the round robin scheduling policy. The source code is shown over here. So, essentially what the XV6 scheduler does is that it parses through the p table array. So, we have seen p table before, which is an array of procs, and the scheduler parses through this particular array and finds the next process that is runnable and invokes the switch. So, this is where you invoke the context switch. So, every time the scheduler executes, the next process in this array that is runnable gets scheduled to execute. So, next we will see scheduling algorithm.